Hello and welcome everyone to electromagnetics lecture again. Time now to take a look at the different kind of coordinate systems that we'll be discussing throughout the whole course. Uh, for the sake of calculation, making the calculations easier depending on the geometry of the physical systems that we will be analyzing, we'll be using these different kind of coordinate system that matches most perfectly with the given geometry. And there are three types of coordinate systems that we'll be discussing. The first one being the Cartesian coordinate system that you are all familiar with. The second one is cylindrical coordinate system that has a lot of similarities with the polar coordinate systems that you are familiar with. And finally, we will learn about spherical coordinate systems that might be a little bit newer compared to the previous two. Okay, let's get started. Let's say you're supposed to calculate the electric field at a given point. Before going into any calculations, you have to first specify that point. To do those things, we use different coordinates. For example, you are familiar with the notations like p, x, y, right? Like let's say p, 3, 4. And you're familiar with this notation. It means going 3 units towards the x direction, then 4 units along the y direction to get to the point, and this is called 3, 4. So this is the Cartesian coordinate system that we're familiar with in 2D space. Okay, so in this course we will have to, however, extend this concept into the 3D space because we will be needing points in 3D space. So we introduce another extra axis that is perpendicular to both x and y axis. So the z-axis is in this picture, it's directed outwards of the screen towards you as you're looking at it. So by now we should be clear that to denote any point in 3D space with coordinates given to it, we will have to first specify an origin point that will be the reference for all the points in the system that we're describing, and then we'll be needing three different axes that will be perpendicular to each other, and these are also called orthogonal coordinate system because of it, because the three axes are perpendicular to each other. That means there are no components of one axis along the others. All right, so when you look at this picture over here, just think of this origin as the corner point of the room you are sitting in. So this is one of the walls, this is another wall, and these two walls are meeting over here along the z-axis uh, in an angle of 90 degrees, right? And also think of this thing, the xy plane, as the floor of your room that meets both of the walls at an angle of 90 degrees. So if we look at it again, this is an angle equal to 90 degrees, though it might not seem like it because this is the 2D picture you're looking at. This is another angle that is 90 degrees, and this angle between x and y axis, this is another 90 degrees. So all of them are perpendicular to each other. The z-axis is pointing uh, along the upper direction on the plane of the screen that you're looking at. The y-axis is directing to the right hand side of the screen you're looking at, and this x is not really on the surface of the screen. This is actually um, moving outwards towards you from the surface that you're looking at right now. So I guess this clears up the direction of the axis a little. All right, so now let's say you have to get to the point P over here. Uh, let's say you'll have to specify this specific point in your room in 3D space that is floating above the ground that you are sitting on. We'll have to specify the position of these points precisely. So let's say we will have to first travel along OX direction for 4 units, let's say. So your travel starts from the origin point and you move along the x-axis. Uh, you travel a distance equivalent to 4 units of it. It might be 4 meter or 4 centimeter or anything. It's 4 units. Then you will have to move along, for example, say 3 units from the point you have reached along the y direction, right? And then you will, let's say you're traveling, let's say you're traveling 5 units upwards along the z-axis to finally reach this point. So the coordinates of this point will be specified by 4, 3, 5. So this is the standard notation you are all familiar with, I guess, right? So this is how we specify the coordinates of a point starting from the origin um, in a Cartesian coordinate system. All right. If you remember from the previous lecture, you will notice that whenever we know the position or coordinates of a point, we also by default know its position vector. The position vector of a point was defined by a vector that starts at the origin and ends at the point that you're trying to specify. So this will be the position vector of the point P. Okay, so one thing to notice over here that OP, this OP vector does not lie on the surface that you're looking at. It actually comes slightly outwards from the surface you're looking at. All right, so we can write OP as 4I, 3J, and 5K. But later on, we will learn about 2 more coordinate systems. So IJK is not going to be a very nifty solution for us. So we are going to change that notation a bit. So we are going to write AX vector, AY vector, and AZ vector instead of IJ and K. And this notation is sort of self-explanatory. So this subscript x means it's the unit vector towards the x-axis, right? So whenever you are traveling towards the x-axis, the unit vector along x-axis will be ax. Whenever you're traveling towards the y-axis, the unit vector will be ay. And whenever you're doing the same thing towards the z-axis, it will be denoted at az. So you don't have to attribute random letters to the axis you're following. So this is a nifty solution for us to denote the unit vectors over here. All right, so the general notation of any sort of vector in 3D space, according to the Cartesian coordinate system, will be like this: ax is a scalar quantity, and ax times the smaller case ax means you will have to travel along x-axis for a distance equivalent to the magnitude of this value over here. Ay is z. All right. And if you were to take the magnitude of a, you will simply take the square root of these things. I guess this is clear from the picture over here. If we go back to it. Okay, let's say OP. The OP vector is actually the A vector we're talking about over here. So we want to take the magnitude of, that means the length of OP over here. So let's say this point over here is A, sorry, let's say this point over here is, let's say M, this point over here is N, and this point is P. Notice that OMN, this is a right angle triangle, right? Because this is a right angle, obviously. If you cannot visualize yet, just note that x-axis and y-axis are perpendicular to each other. So this line, the MN line, is along OY. So this is perpendicular to OX. All right, so OMN is a right angle triangle. So obviously ON squared, sorry, ON squared equals to OM squared plus MN squared. OM is the x coordinate of P, right? All right. And then if you look at this triangle over here, the OPN right angle triangle, because PNO is a right angle over here. So you'll get OP squared equals to PN squared plus ON squared. But you also know from over here, ON squared is equals to x squared plus MN squared. But PN is parallel to the OZ point. Let's name it L. So OL is the distance that you have to traverse from XY plane to get to the P point, right? The elevation of the P point from the ground. So OL is the Z coordinate of P. So this makes it Z square, this is X square, and MN is the y coordinate of P, right? So this is y squared. So OP, that means the magnitude of A will be equals to x squared plus y squared plus z squared, right? And these AX, AY, AZ are the same thing as these AX, Y, and Z. We'll have to talk a little about the unit vectors over here. We have to know what they mean. Well, the standard notation of unit vectors are smaller case a cap. You can write ax cap, ay cap or something, but you can also write ax bar. So the notation won't be a problem, but you will have to know that by convention, we denote the smaller case letters as the unit vectors, all right? And the Cartesian system is not that hard to get your head around because you're familiar with all of these things. Note that Cartesian coordinate system is also called a rectangular coordinate systems, and that because uh, the x coordinate, the y coordinate, and the z coordinate, they kind of together they make up the three sides of a parallelopipe. All right. So it looks kind of like this. As the three coordinates set up the three sides of a parallelopipe, so this is also called a rectangular parallelopipe, to be more exact. This is also called a rectangular coordinate system.